course in AFDX is going to be divided into 4 parts. The first part is going to be not about AFDX at all, but about Ethernet, upon which AFDX is based. Because without understanding some basics of Ethernet, it's kind of difficult to get into AFDX. And as I have no idea what anybody understands, I'm going to tell you what I think is the most basic parts, which probably does not match what most people think are the most basic parts, but I'm gearing it towards what we need for AFDX. Then, once we understand a little bit about Ethernet, we'll talk about the difference between AFDX and Ethernet. After that, we'll go into what the AFDX spec says, and finally, we'll go into implementation issues, which focus on the things that the spec does not say, but on how it is that you actually implement it and what the various options are. And hopefully, by the time we're done, you'll have a pretty good understanding of why the Boeing and Airbus chose AFDX, what it's capable of accomplishing, and how it can be used. So we'll start with the basics of Ethernet. And when I talk about basics of Ethernet, what I'm really talking about are the packet structures. Because the way Ethernet works is, right, you're familiar with it from work and reading the newspaper. Well, I usually use reading the newspaper as a good example because it's a very popular thing to do with the Ethernet. And the idea is that you need some way of connecting yourself to whatever newspaper it is that you're interested in reading. And that newspaper may be 10,000 kilometers away from wherever you are. So how is it that the information that you're looking for gets to them and the information that they have gets back to you? And the way that's done is through a packet, right? Ethernet sends and receives packets. And each packet is itself comprised of a number of headers. So let's look at what kind of headers we have. And not every packet is the same as every other packet, but I'm talking about the kinds of packets that are most frequently used for sending data from one place to another, because that's the most common use in AFDX. So it turns out that there are 3 different packets that are used in standard Ethernet and in AFDX for moving data. And the first packet, the first header rather, is called the MAC header, and it contains the physical address of the NIC, or network interface card. That's the physical card in your computer that you plug the Ethernet cable into. Now, there are, of course, probably hundreds of millions of these cards out there, and every one of them has a different address, right? So obviously this is done when a manufacturer wants to make a card, he has to go to a centralized organization and get a list of numbers that he's now entitled to use. And then he puts each card he gets is a different number. And that way, when you're trying to communicate with somebody, they know exactly who they are and you know exactly who you are because you've got this different address. Now, this header address is 48 bits long. And for those who are curious, 48 bits is like 17 gazillion different numbers. I don't know what the exact number is, but it's 4 billion times 64,000, roughly. So it's a very, very large number, which makes it possible to get everybody their own number. Okay, so that is a part of it, but it's not quite enough because given that there are hundreds of millions of these cards out there, how do you know where to go? Where is that header? So we have another header that goes past that header, well, which is the IP header. And the IP header is more of a logical address. And there's a difference between a physical address and a logical address, because a physical address actually is associated with a physical card, whereas a logical address is going to be associated with maybe a company. So to take, for example, if I want to read the New York Times. New York Times and there are different ways that this can work. New York Times has many, many computers that contain, that are servers that can give you the paper. Now, each one of these computers has its own network interface card, but New York Times is the New York Times. They have one address. So the IP header points to the New York Times. Now, and so in this particular instance, your interest as somebody who wants to read the paper is really the IP address of the paper. You don't really care which server you get it from. And it could very well be that you could get it from different servers all the time. But you want the New York Times, which is the IP header. Then you've got case of phone companies. You know, a phone company works somewhat different. Does it really? Well, there again, you're dialing when you dial a phone number, really who you're dialing is the phone company. And then the phone company is going to connect you to the other side. So here, yeah, you'll probably also have one IP for the phone number, and then they'll send you to the various ones. In any event, you need both of these addresses. And then finally, you've got a TCP or UDP header, which is where the actual, well, we'll get into this in a minute because we're going to look at each of the headers separately. The MAC header only contains 3 fields: the destination address, the source address, and the type. Destination address, if I'm trying to get onto the New York Times, is the New York Times. The source address is me. On the other hand, when the Times responds to me, it's going to flip these 2 addresses. I become the destination, and it's the source. And the type is the way you know what is the next header that you're going to see. So in our case, the type is going to be an 800, which is an internet protocol, which means that the next header is going to be an internet protocol or IP header. There are other kinds of headers. For example, an ARP, I don't know if you're familiar with it, but an ARP is a way of, if I know an IP address, how do I get the MAC address? Right, so I know the logical address because I know that I want the New York Times. And the New York Times is on many, many, many lists that are available all over the place, telling you what its IP header is. On the other hand, the individual servers inside the New York Times, those NICs, the cards, they could change on a daily basis, right? People are constantly changing hardware, and that information is not as easy to get. So what you do is you ask, using what's called an ARP request. You say, listen, I know the IP address. Please tell me what is the MAC address associated with it. And that's going to be an ARP reply. And if you've heard of ping, then what a ping does is now that I know your MAC address and your IP address, I want to see, are you up? Are you available? So I send the ping, which is just exactly that. It's a ping, ping. And it's basically a request of saying, if you're there, respond to me. And then you get a ping respond if it is there. And if it doesn't respond in a certain amount of time, then you know that it's not up. So that's another kind of type. Our type is an 800, which is an IP type. So we get to the IP header. And the IP header is considerably more complicated than the MAC header. The last 2 fields on the bottom here, source address and destination address, are very parallel to the MAC header. That also has a source address and a destination address. As I mentioned, the MAC addresses refer to the card, whereas the IP addresses refer to the logical entity, as in the New York Times or the Guardian or the Build or whoever it is that you're interested in reading. So that is that's the part that is parallel. We'll briefly go through the other headers. Actually, let me just double check what's next, right? And right, okay. So we're going to go back because very often I just forget what's on the next slide, and so I describe things on the front slide that I don't need to. But okay, so the IP header is 20 bytes long. The first, and I'm talking now, there are 2 versions of IP headers, of course. There's IP4 and IP6, which I understand isn't logical because I don't know what happened to 1, 2, 3, and 5. Or actually, I kind of do. And I'll tell you. Version length is the very first byte, which means 1 nibble, 4 bits a piece for 2 fields. The first field is the version number, so that's the 4, and the 5 tells you the length of the of this header, which is, and it's a 5 because it's 5 double words, 5 4-byte words, meaning it's 20 bytes. Now, the reason that it's called version 4 really is because the address, if we go back down to the source address and the destination address, these addresses are 4 bytes. In IP version 6, there's 6 bytes. Now, most of the world is still in using IP version 4, but we're slowly moving to IP version 6. And the reason is that 4 bytes gives you 4 billion possibilities. 4 billion sounds like a big number, but we're using them up. And part of the reason that we're using them up is because there aren't actually 4 billion different users. I mean, there are 4 billion people there, but there aren't 4 billion New York Timeses, or things equivalent to them. However, a lot of the numbers are wasted because, like, large companies get, you know, tens of thousands or hundreds of thousands of numbers, and numbers are reused all the time. The point is that they're being used up. So by adding another 2 bytes, that multiplies the number of addresses by another 65,000, and that should cover us for the foreseeable future. Although with the Internet of Things, we will probably get there eventually too, because now every Coke machine has its own IP address. Okay, anyway, the second, going to the next field is type of service. Type of service could be what's in the packet, right? Is it a video? Is it a voice over IP? Is it data? And the reason that this could be important is because there's this notion of fairness. Now, fairness means, well, I don't know what fairness means, to be honest. It means different things to different people. So one notion of fairness is that everybody should be exactly the same. The problem with this notion is that everybody is not exactly the same. So another notion is that everybody should get what they need. For example, if you're watching a video and your packets don't come quickly enough, you can't really watch. It's not, it's going to be jumpy. On the other hand, speech, you also don't want it to be jumpy, but the human ear is just not as quick as the human eye, and therefore, for a video not to be jumpy, it has to come up you need a new screen every 30 milliseconds. For voice, it can be a lot slower. For data, it could be a lot slower than that. Right now, so if you're reading the paper and you click on a link and it doesn't load instantaneously, which of course it doesn't, that's okay. You can put up with that. It doesn't make it harder to read. It just makes you have to be a little patient. Whereas if you're watching a movie, it makes it hard to watch. So the argument could be made that video should be given preference. It is, in fact, a large political debate all over the world whether we should do this or not. But if you do want to do it, that's the field that you use. Okay, following that, you have the IP packet length, and the IP packet length tells you how much data there is starting with this header until the end of the packet, including the data. Since a Ethernet packet can be up to a little over 1,500 bytes long, this number is going to be somewhere between, well, 64 usually is the minimum packet length, and 1,500. It's actually be a little less than 64 because it doesn't count the MAC header, right? The MAC header, which is, we said 3 fields, 2 6-byte fields and a 2-byte field. So that's 14 bytes, is not included in this number. Okay, there's an identification, which we'll get to later, fragment field, which we'll get to later as well. Time to live is an interesting field. Time to live is a number, it's often given something like a 32 to start with. And every time this packet is sent somewhere, or passes through a switch, it gets reduced by 1. And remember, if you're in your office and you want to get onto the Times, so in your office itself, you have a switch. And that switch will connect, if there are a lot of you in the office, you'll all be connected to one switch. And that'll forward you to whoever your internet provider is. Often it's the phone company. Sometimes it's a satellite company. It can be a cable company. So that's your first switch. When your data gets to that switch, it's going to reduce the time to live by 1. It's then going to send it over the phone or the satellite or the cable to whatever company is on the other side of that. So let's say it's the phone company. It'll get to their switch. It's going to reduce it by 1. Then the phone company is going to forward it to some other company who's responsible for underwater cables. They have a switch that reduces it by 1, and onward and onward. And if it goes through 32 different switches, it dies. Meaning that we expect you to get to wherever you're going in a lot less than 32. The problem with standard Ethernet is that we don't know how many it's going to go through. And it might go in a loop. Now, let's say somebody has a poorly programmed switch. Well, if that switch sends it back to a switch where it's already been, then it'll go ping pong between the two of them forever, and it's taking up resources on both of those switches. And in order to avoid that, we say, well, if it went more than 32 times, probably it got messed up. It's never getting where it's going anyway, so let's just get rid of it. And we'll see soon why that can happen. Okay, then you've got a byte telling you the protocol. Whoops. Because there are, in fact, many protocols that are available. And we're going to be discussing UDP and TCP, which we'll get to. Then there's a checksum. Now, a checksum is the checksum of all the other fields in the IP header. That way, when you get to the other side, right, whoever's supposed to be getting this packet, he'll check the checksum. And if it's so the checksum is an algorithm, a fairly complex algorithm, that you take all of the bytes until now, put it through this algorithm, and you come up with a number. So when the transmitter transmits the packet, he does that. When the receiver gets the packet, he does it again. He takes all the fields other than the checksum, and then he sees if it matches the checksum. It might not, because it's going through a lot of different equipment, some of which is perfect, some of which is not. It's going through wires, some of which have noise near them, some of which do not. And so mistakes happen. And the important thing is to catch them when they happen, right? You can't make them not happen at all, although you can do your best. But but equally important to trying to make them not happen is dealing with it when they do happen. And the checksum allows you to deal with it. Now, what do? Let's say your checksum says that the packet is bad. What are you supposed to do? So now we'll discuss the difference between UDP and TCP. In TCP, every time a packet is sent, it expects to get a packet back saying, I got your packet and it was okay. It's called an acknowledged packet or an ACK. If the receiver looks at the checksum and sees that the checksum is bad, he will not send the acknowledge. And then the sender, after waiting for a certain amount of time for the acknowledge, realizes that it didn't happen, and he'll resend the packet. This is part of the TCP protocol. Under UDP, you don't do that. UDP, there's no acknowledge, and therefore the transmitter will never transmit again in case of error, because there's no way of knowing that there's an error. He sends the packet and hopes for the best. Intuitively, one would think that on an aircraft, you would want to be using TCP. You'd be wrong. And hopefully we'll see why later. But in fact, well, actually, I'll tell you now. Okay, you forced me into it. The reason is that while TCP is a lot safer, it's a lot more unpredictable in terms of its timing. And it turns out that on an aircraft, even more important than the data getting there correctly is it getting there on time. And in order to predict the timing, we have to know in advance how many packets are going to be sent. So if you just arbitrarily let people do retries whenever they want, then that's going to be very problematic in terms of time. Now, obviously, you have to deal with the problem of what if it's not getting there. So there are other ways of doing that. For example, you can develop at a higher level. You can have a handshake, not part of the IP protocol, but at the application layer. The application will send a message, and maybe it'll get a message back. And if you do it at the application level, as opposed to the low TCP level, then you get to choose for each bit of information you send, do I really care if they got it or not? Because a lot of information, if you miss it, none's going to happen. There's a lot of information on an aircraft is being sent every 30 or 50 milliseconds. And if I miss one, I'll just get it the next time. So I may not care that much. I don't want to know periodically, like once a second, I'll do a health check, say, to see if you're getting anything. But I don't care if any particular packet makes it or not. On the other hand, I very much do care that the packet go out every 30 milliseconds. I'm assuming that 99.9% of the time it's going to make it anyway. So that's why the timing just is more important than the correctness. Okay, the last header that we need to talk about is the UDP header. Now, going back to our example of a newspaper, so we said again, the MAC address is the physical card that is that I'm talking to. The IP address is the logical entity, as in the New York Times. The UDP is there to tell you which page of the paper I'm looking at, right? Because I could have 5 different tabs open in my browser. Each tab will likely be a different UDP address, even within a tab. So I have like 4 advertisements that I can click on and get somewhere else. Each of them is going to have a different UDP address. So the UDP address is not directing me to a particular computer. I'm already on the computer because of the other 2 addresses. The UDP is really more of an application kind of a thing. What within the computer am I looking at? And that's done through a UDP source port and destination port, which essentially is the parallel of the MAC address and the IP address. But because it's not really an address, because I'm already on the computer, we call it a port. Then we have a UDP length, and the UDP length is the same concept as the IP length. Namely, it's the length of from this header on till the end of the data. And since it includes the UDP header but not the IP header, whereas the IP length included the IP header as well, the IP length is always going to be 20 bytes longer than the UDP header. So that's just a kind of a check that you can make. Okay, and the final field is a checksum, and this checksum very often is not used, in fact, because this would be a checksum of all the data. I hope that's not too disturbing. Anyway, problems of working from home. Right. The IP had a checksum, but that was a checksum just of the header itself. It's only a checksum of 20 bytes. Whereas this would be a checksum of the entire data. So it's a useful thing to have because you want to know if the data is correct, but it's expensive because it turns out that figuring out a checksum takes a lot of resources. And if you have to, the more data you're doing a checksum on, the more resources you need to spend. So sometimes it's used, sometimes it's not. Okay, so now I promised before in the IP header that we'd get back to a couple of the fields, namely the fragment field and the identification field. So we'll start with the fragment field. Fragment field is 16 bytes long, and why do we need a fragment field? Sometimes you've got to send something, and if I'm going to borrow from AFDX, I'll say there are kinds of messages on AFDX that can be up to 8,000 bytes long. But physically, a Ethernet packet is only allowed to have up to about 1,500 bytes. So how do we handle that? So the answer is we can break a message into sub-messages called fragments. Now, in the old days, I don't think it happens so much more, but in the old days, there was different kinds of equipment on the way, on switches that you have to go through, which handled different size packets. Originally, switches all handled 512 byte packets, and they went up to 1,024, and then went up to 1,500 and something, 72, I think. And so what if you're sending a 1,500 byte packet, but you came across a switch that doesn't know how to do that? He only knows how to handle 1,000-byte packets. So then he would have to break it up into 2. And this is the mechanism used. So you have this fragment field contains 4 subfields, one of which is not used, so that's simple. The next bit is don't fragment. So that's telling this switch on the middle that if you can't send me as I am completely whole, don't bother, just throw it out. Under the assumption that the next time I send it, it's going to not go to you. It'll probably go to a different route. In fact, maybe I'll even instruct my, there's a lot of logic going on in the different switches, telling each switch where to forward it to. And at some point, if there's one switch that can't handle fragments, then the switch in front of it won't send it packets that are too large. So this bit says, I do not want this one fragmented. The next bit says that, and you're never going to set both of these at the same time. So bit 2 says, this is a fragment. And as when you get this packet, it's not done. There's more and you got to wait for it. And then the last field is already a larger field, and that tells you the fragment offset. So that's saying if on the first fragment offset is going to be 0, right? It means where do you put this fragment in the final message? Is it the beginning? Is it the middle? Is it 2/3 of the way in? Is it the last one? So by getting the fragment, then I know exactly where it is. Fragment offset is a 0. So if you have fragment offset 0 and bit 2 is a 1, that means this is the first fragment and there are more to follow. On the other hand, if bit 2 is a 0 and the fragment offset is not, that means that this is the last fragment. Because it can't be the first, because the fragment offset has to be a 0 on the first. And it can't be in the middle, because if it were in the middle, there would be more fragments, but bit 2 is 0, so there aren't more fragments. And then, so assuming now, just to round the numbers a bit, that the maximum that you can put into a packet is 1,500 bytes. So then the first fragment will have an offset of 0, and the second fragment will have an offset of 1,500. If we want to get technical about it, the fragment offset actually has to be divisible by 8. But in any event, but that's really a tiny detail. So the first fragment will be 0, the second will be 1,500, the third will be 3,000, then 4,500, and so on until you get to the last fragment. Okay, now when we do send fragments, every single fragment has to have a MAC address and an IP address because it has to know where it's going. So you can't let up on that, but it doesn't have to have a UDP. And the reason is because all fragments of a message have the same IP identification. So when it gets to the final computer, and the final computer is wondering, all right, which one of my tabs on the Explorer is this going to? It looks at the identifier. And it says, oh, okay, I've gotten this identifier before, and the first fragment had a UDP header, so I'm going to look for it. So that's what the identification field is for. It's basically to distinguish between messages. And so it always changes between messages, but within a single message, and I'm calling a message the full thing that you want to send. So if I have 10 fragments, those 10 fragments together make up a message. If I have no fragments, then a packet equals a message. Okay, so that's the fragment field. Now, within the IP protocol field, so that you could have UDP or TCP. You can also have IGMP, ICMP. There's like a host of others. Pings, for example, are ICMP. And most of the others are used for housekeeping kind of things, seeing who's around, finding out what their addresses is, that kind of thing. Okay, now the time to live we discussed before is that every time it goes through a switch, it goes down by 1. And the reason for it is to prevent loops. And why might there be loops? Because this is a map of just undersea cables. Now, undersea cables, as you might imagine, are extremely expensive to put down. And therefore, there are going to be a lot fewer of these than there are of all kinds of other switches. And there are a lot of these. So you'll see here that, right, this is the east coast of the United States and the west coast. And there's a lot there, but it seems that there's a lot more here in Europe and in the Far East. You've got also a huge number. So there's just a lot of these things going on, and which means that there are probably hundreds of thousands of, or certainly tens of thousands of switches on out there. And each switch has to know where to go next, right? So if I send something to my office switch, it has an easy job because everything it gets, it sends to the phone company. But but the phone company now has to send things all over the world. So it has to be smarter than my switch, and it has to, for every address that comes in, it has to know, well, which of the other switches out there can handle that address. And that's what things like ICMP and IGMP, those other protocols are for, is to ask the other switches, well, who do you handle? So each switch is going to do this periodically, find out from all the switches that it's connected to, who do they handle? And that way it knows when an incoming packet comes in, who can it send it out to? But this is a very complex mechanism, and it sometimes messes up. So you could easily have switch A sending something to switch B, which sends it to switch C, sends it to switch D, which then for some reason sends it back to switch B. And then it's going to go from B back to C because it did it before. Why shouldn't it do it again? And it could loop forever. And that's why we have this time to live to avoid that happening. Okay, so getting back to the switch, a switch has input ports and output ports, right? The data comes in through the input, goes out to the output, except it doesn't have one of each. It can have many of each. So the switch takes from any of its input ports, it gets a packet, and then it has to figure out which output port to send it to. And I write here, it routes it to the appropriate output port. Now, appropriate is a vague word, not something that one would use in a specification. And what it means is two things. First of all, it's got to be a port that's going to get you closer to your eventual destination. And second of all, it's got to be the fastest way to do that. So I might be connected to 10 different output ports, all of which will get me one jump closer to the New York Times. Okay, so which one do I choose? And the answer is, it'll depend. Of the 10, I can really send it to any of them. So what I'm going to do is I'm going to see how busy are each of the ports. Because this port doesn't only send to the New York Times, it also sends to 10,000 other websites. So some of them might have a lot of traffic going through them, and some of them may not. And this can change second to second. And so what I'm going to do is I'm going to see, well, how busy is this output port? And why don't I send it to the one that's least busy? Which means that if I'm reading something for an article on the paper, and it's a long article, it's going to require multiple packets. I might get one packet with one set of switches, and the next packet is going to be a totally different set of switches, which means that I might get the second packet first. Right? So the Times may have sent me a message with a bunch of fragments, and the fragments each got routed differently. And when they came to me, they came in the wrong order. So my computer is going to be smart enough to not send me any of the data until it gets all the parts. And so I won't get things out of order. But things can go in different paths is one of the points I want to make, because this turns out to be important when we discuss AFDX. Okay, so that's probably more than you ever wanted to know about Ethernet headers. So I'm going to now back off of this and start talking a little more about AFDX. So I'll talk about right now focusing on the difference between standard Ethernet and AFDX and decisions that had to be made. Okay, so in standard Ethernet, the source and destination addresses are unique. There's in the MAC address, we said that 48-bit address is different for every single card. Okay, well, how did that happen? It happened because there's an organization called the IEEE, and they own the MAC addresses, and they sell them to whoever it is that wants to build NIC cards. So that way everything is unique. And the reason that it's important to be unique is because anybody in the world can theoretically talk to anybody else in the world, and therefore they all have to have their own unique address, just like everybody needs their own unique telephone number. So comes AFDX and says, well, our needs are somewhat different. I'm only trying to communicate with other boxes on my airplane. I'm not going to crash into somebody on a different airplane. I don't care if he's got the same addresses as I've got. I just don't want to have the same addresses on my airplane. And therefore, the source and destination address are going to be somewhat different. I don't need nearly as many bits. I'm not planning on having 17 quadrillion boxes on my aircraft. So therefore, first of all, we don't use all the bits. The high 24 bits are just fixed. Now, AFDX is dual redundant, which is something that we'll get to. We'll talk about more. But I want one of the bits in this header is saying which bus am I on. Right? I'm going to have 2 separate wires for every single message that I send, so that if there's a problem with one, I don't lose it. Right? If there's a problem on a wire somewhere on the way between the New York Times and myself, all right, I'll get a little gibberish somewhere. Happens all the time. But if it happens on an airplane, bad things could happen. So I want dual redundancy. So that's one bit I'm going to use for dual redundancy. Then I'm going to have a whole bunch of other bits that don't matter. And the important bits are this thing called the VLID. So the VLID is the equivalent of the address of where it is that I'm sending this data. But interestingly enough, as opposed to in the Ethernet world, where I want it to be unique, here I don't want it to be unique. Because if I'm sending, for example, the data that I'm sending is altitude, it could be that there are 5 different devices on the aircraft that need to know the altitude. And therefore, I don't want it to go to one place. I want it to go to any place that needs to know altitude. So we call that a VLID, or a virtual link identifier, is the address. And it goes to it's a functional thing. It goes to whoever needs this information. So that's the MAC address differences between standard Ethernet and AFDX. If we move to the IP address, so the IP address, again, in Ethernet, they're unique. Here, it's not the IEEE that gets to assign them, but another international company called IANA, or the Internet Assigned Numbers Authority. So again, you've got these unique addresses. Now, Ethernet has a number of different modes in which it uses. You can send data to one specific address. You're allowed to send a broadcast. And you can send what's called a multicast, which means that I want the same data to go to 8 different places, for example. So in AFDX, there are only a very specific number of source addresses that are used, and they're all what's called private network. Because in Ethernet, we also recognize that if you're talking within your office, and if this is data that's not meant to go out to the Times, but it's meant to go to a coworker, then you can reuse the same addresses as the guy in the office next door, because these are internal. And so you're having a set, and he can reuse the same set. Those are called IP private addresses, and that's the only kind that we use in AFDX, right? Because AFDX is not used to communicate from one plane to another. Turns out that the wires make it inconvenient to do that. In addition, IP destination addresses always use multicast, because that's the nature of what we just described as a VLID, that a VLID may go to multiple boxes. And therefore, that's the kind of thing that we do, and therefore they're not unique. So the altitude information might go to a screen that the pilot can look at. It might also go to the autopilot. It might also go to the black box. In fact, it'll almost certainly go to at least those 3 things, and possibly quite a few others. So we don't have this point-to-point concept in AFDX, but rather one transmission can go to multiple destinations. Okay, so what's the difference between an Ethernet switch and an AFDX switch? So what an Ethernet switch does is it takes the incoming packet, looks at it, and then sends it out to one output port. Whereas an AFDX, it may send it out to multiple output ports, right? Because it's going to multiple devices. Now, in Ethernet, as we described before, there could be many ways to get from a source to a destination, because each switch can choose between among 10 different output ports that it's allowed to use to get to that particular destination. That doesn't happen in AFDX. In AFDX, the switches are defined so that there's only one way to get from any source to any destination. Now, this has a plus and a minus from a security point of view. The plus is it simplifies things enormously if there's only one path. The minus, of course, is that if there's a problem with that path, it's not going to get there. But because of that, and because there's in general a problem with airplanes, that you need things to get there every time, as we introduce dual redundancy. So Ethernet does not have dual redundancy. Typically, your computer has a single Ethernet port that you attach to your wire, which is attached on the other side to your switch or your hub. Whereas AFDX always has two. So that's dual redundant. And in Ethernet, you have this notion of prioritizing messages. AFDX, it doesn't exist. And the reason that it doesn't exist is because you really only need to prioritize things if you don't have enough time to do everything. Now, in the real world, in Ethernet, when you've got billions of users, there's never going to be enough resources to get everybody instantaneously everything that they want. We're getting closer and closer, but it's not going to happen. AFDX, it can happen, because AFDX, we know when we build the plane exactly how many devices are going to go onto this AFDX switch, onto the whole network, and we know what the data requirements of all of them are. And if we build our plane intelligently, we'll make sure that all of the data requirements fit into the time that they have. So in other words, if you've got a device that needs to talk for 10 milliseconds out of every second, right? So that means it needs 1% of the bandwidth. Okay, I can have up to, theoretically, 100 devices like that, and they'll all work harmoniously. But if I have 101 devices like that, I've got a problem, because then I've got 1.01 seconds worth of data that I would like to transmit every second. That's not going to work. So I don't design the plane that way. Now, let's say I've got all these boxes and I absolutely need that to happen. All right, so I won't use one AFDX networks. I'll switch it into two AFDX networks. Not that that's necessarily a simple thing to do, because if there are two networks, then some of the boxes can't talk to other of the boxes. Work it out. Not every box on a plane has to talk to every box on the plane. All right, in terms of timing, Ethernet, there's just nothing defined. The Ethernet spec is called 803.2, and it says nothing about when you're supposed to send the packet, right? Because it's not going to tell me that I have to read the New York Times today. Obviously, from the New York Times perspective, they'd like to respond as quickly as possible, or I'm going to start reading the Wall Street Journal. But there's nothing in the spec that tells them that they have to. AFDX is exactly the opposite. I'm on a plane, right? The pilot wants to know the altitude, and he wants to know it frequently. He wants to know the latitude and the longitude. So data on a plane tends to be time critical all the time. And the only way that I can do what I described in the previous slide, which is make sure there's enough time, is if I know exactly how much time each device is going to take. So we do that with something called a bag. I'll get to what the bag stands for in a minute, but the idea is that every VL, and a VL represents a kind of data, right, like altitude. So for the altitude, I say, all right, the altitude has to go out every 16 milliseconds. The status of the landing gear doesn't change all that often. I'll throw that every 128 milliseconds. If I'm my radar, on the other hand, which is telling me about some dangerous thing that's in front of me, I want to know that every millisecond. So I get to choose for every kind of information how often it gets transmitted. And the range is every millisecond to every 128 milliseconds. Now, obviously, these are the things I'm going to play with. How frequently the data goes and how much data has to go out with that frequency. And if I multiply the amount of data times the frequency, that tells me the percentage of the bus that I'm going to take up. And when I do that to all of the devices on the bus, that tells me the total throughput of the bus. Okay, Ethernet has a plethora of different protocols. Many of them have to do with housekeeping in order to make sure that all the switches are properly programmed, that everybody knows all the changes that are being made in real time. Most of this is unnecessary on an airplane. Changes are not made that frequently. When they're made, I can just physically reprogram the switches. There are just almost all of this stuff turns out to be pointless on an airplane, and therefore almost all of it is not used. UDP is the most used by far type of packet on an airplane. Okay, so those are the key differences between AFDX and Ethernet. And now that we know the differences, it may seem counterintuitive, but now I'm going to go into actually what is AFDX. Because I've been talking for a while, but I really haven't said much about how AFDX itself works.
Maybe we take a break now?
Sure, why not?
Okay, everybody, take 2 minutes, have your cup of coffee, do what you need to do, and we'll be right back.
Okay. Which is an organization comprised of the airplane manufacturers and a lot of the airlines, in order to, their purpose in life to put out specifications that everybody can agree on, which makes it easier for people who are manufacturing devices for the airplanes, like engines, for example, or radars, or landing gear, or screens. And it makes it a lot cheaper for the manufacturers and therefore for the airlines, since they don't have to worry nearly as much about compatibility issues. It was called AFDX originally by Airbus, who invented it, and in fact, there's a it's patented and trademarked. So you've got to actually pay somebody if you want to use AFDX on your product. Anyway, just a fun fact. Why is it that Airbus decided to come up with this spec and Boeing eventually joined with them in developing the new specification for aircraft? Aircraft have been using digital buses for quite a while, starting with the various ARINC specs in the 70s, actually. So why is it that they needed a new one? All right, well, ARINC-429 is old, and it dealt with very small amounts of data, whereas the newer aircraft have just massive amounts of data, so they needed something new. Now, they tried about 10 years ago, 15 years ago, they actually tried to develop their own spec from scratch, and it was called the ARINC-629. And again, both Airbus and Boeing were involved, and it was a totally new specification, fairly complicated. And they figured they're the two largest aircraft manufacturers on the planet. Whatever they say, people will do. Turned out they were wrong. And so not that many people joined them. And those that did usually had a monopoly on whatever device they were producing, because there were just not that many companies that wanted to produce any given 629 device. And of course, that made the costs go through the roof, because when you're a sole manufacturer, you can kind of demand whatever price you want. So it took a while, but they learned from their mistake. And the next time that Airbus and Boeing wanted to do something like this, they said, you know what, instead of starting from scratch, why don't we take advantage of off-the-shelf technology? Right? And off-the-shelf technology means that everybody's willing to do it. Everybody already knows how to do it. Plus, you don't have to do that much development. The development's already been done. So that was what they wanted for this new spec that they wanted to have. They wanted to take advantage of off-the-shelf technology. However, they wanted to make sure that it had guaranteed real-time operation because this is an airplane. And if something takes a little longer, it matters, which is not necessarily the case with all other kinds of networks. Now, the data types of things used on a plane are somewhat different than data used in other areas. And there are two kinds of data, one of which is very repetitive. Altitude, latitude, what we call engineering units, is the kind of data that's going to be sent over and over and over again every 30 or 50 milliseconds. So many times per second. That's the specific needs of an aircraft. Now, there are also other kinds of files needed on an aircraft, which might be large files that are sent in, not periodically, right? If you're sending a database, so then every packet you send looks different than the packet before. You're sending a large file. If you're sending a movie, so you might be sending tens of thousands of packets, all of which are different, as opposed to the previous kind of data, the altitude, latitude data, in which the format of every packet is the same. The first 4 bytes are going to be altitude. The next 4 bytes are going to be latitude, and onward and onward. The contents will change, or we wouldn't bother sending it, but the type of data is not going to change. So these were their two needs. They wanted to be able to send data that does change and data that doesn't. Okay, so in order what they decided to do on this is to base it on Ethernet. Ethernet is a very smart choice because there are billions of users, and there are just such a huge market that there are constantly more developments of new things. So that whereas Ethernet, even 10 years ago, a gigabit was considered a big deal, now 10 gigabit is in wide use, and 100 gigabit is beginning to enter the industry. And they don't have to do any work for that. They just get that for free because there are so many others in the industry doing this on basic work. Okay, so they could base it on Ethernet, but they had to fix some of the problems with Ethernet, or not really so much problems as some of the aspects of Ethernet that were not appropriate to airplanes. The first one of which is real time. Ethernet is fast, but it's not real time. The definition of real time, by the way, means fast enough to do what you need it to. Right? It doesn't mean it has to get there in a microsecond. If you need it in 10 milliseconds, that means it has to get there in 10 milliseconds. But it means that it always has to get there within 10 milliseconds. So as opposed to Ethernet, where you'll complain one day that the Ethernet is slow, and you'll be right, that can't happen on an airplane. It's got to be the same every day. Now, in terms of the types of data, so they divided into multiple, there are different types of data you can send over AFDX. One of them is called sampling messages. The other are called queuing or SAP messages. These are similar messages that have different purposes. Now, sampling and queuing is actually defined in a different ARINC spec, I think ARINC-453. And they co-opted this into AFDX. So the definition is somewhere else, but they said this is what we're going to use. Okay, so now let's talk about each of these things. How do you make Ethernet real time, right? How do you not have a slow day? So the first thing they did was say, all right, there's only one path from source to destination. I know exactly how it's going. The switch doesn't have to make decisions. It's not going to be different in the morning and at night. I know if I send this, it's going to go from A to B to C, and that's it. Right? Because different paths are going to take different amount of time, and that's what we're trying to avoid. Next, you have smart switches, which are going to buffer and route packets, which is not that unsimilar to Ethernet, but the switches are custom made, largely because we talked about having a single input going to multiple outputs. So they put a lot of the intelligence of the AFDX network into the switch. And in fact, the specification for AFDX has two parts to it, one of which is for people developing end systems, an end system being an engine or a radar or a landing gear, and the other half is people developing switches. And the third thing that they had to do is limit the bandwidth. Not everybody can send whatever they want. And standard Ethernet, I can do whatever I want. If I want to if everybody in my office decides to download a movie at the same time, then we're going to crawl to a halt. So they don't allow me to do that. They say, you've got to tell me exactly what kind of data you want and how much time per second you need it for, and that's how much you're going to get. And once we make that decision, you're not allowed to take more than that. Okay, we talked about a virtual link, and I'll show visually what it means. So as we said, boxes are called end systems. And if we look down at the bottom, I'm talking about end system 7 in both cases is my example transmitter. But there are two kinds of data that it's sending out. We'll call one type of data VL5, or virtual link 5, and the other kind of data is VL6. So let's say that end system 7 is an inertial navigation system. And as an inertial navigation system, it has to transmit the latitude and the longitude and the altitude and a host of other things. Now, it could be that some devices need to know the latitude and the longitude, and other devices need to know the altitude. So the switch is the one responsible for figuring this out. End system 7 sends VL5, which say is the latitude and the longitude. The switch knows that latitude and longitude, of course the switch doesn't know that that's what we call it. It knows that it's VL5 because VL5 is in the IP address, and for that matter in the MAC address. And so it looks at that and it says, oh, okay, VL5, let's send you to output ports that are connected to end system 9, 15, and 18. Whereas if the same switch gets a packet from end system 7 that contains not latitude and longitude, but rather contains altitude, and it knows that because it's VL6 in the IP destination, then it's going to send that to ES9 and ES12. So ES9 is getting both of these pieces of information, but in addition to ES9, in the case of the latitude and longitude, it's going to 15 and 18. And in the case of the L6, it's going to 12. So the every end system can put out multiple VLs, multiple types of data, in other words. And each of these types of data can theoretically go to a different set of end systems on the plane. Now, you're allowed to have more than one switch on an aircraft. And the way you're going to determine your switches is really, it's a topographical issue. You want to minimize the wiring. So let's say you might want to have, on an aircraft, you're going to be wiring from the cockpit to the tail and out through the wings. So it makes a certain amount of sense to have a switch at the beginning of each wing, right? Because then you only have your bus wires to that switch, and then that switch is going to wire to the various things on the wing. As opposed to if you didn't have, if you had your only switch was in the cockpit, then you need to draw multiple wires from the switch to each wing. And that's a lot of weight. Whereas if I put the switch at the beginning of the wing, I only need one wire going from the cockpit to the wing, and then I have multiple wires going the shorter distances on the wing. So that's just an example, obviously. So you're going to make this decision based on how you can limit your wiring and yet not have too complex a network. So here is an example where end systems 7, 9, and 18, and 15, actually everybody, all of the end systems are connected to switch 1. Now I put in the switch 2 on the top there. No, actually no, right. And switch 2 is only connected to end system 3 and switch 1. So this turns out to be illegal. Why? Because how do I get from end system 7 to end system 3? Well, it turns out I have two ways of doing it. End system 7 always sends directly to the switch 1, but switch 1 can send either to end system 3 or to switch 2, which will then send it to end system 3. But we just said you're not allowed to have two possible paths, and therefore you're not allowed to do this. Now, that's not to say that you're not allowed to have these wire connections. That you are allowed to have. But if you do have them that way, then you have to inform switch 1 that it's not allowed to send anything to end system 3. Anything that it has that's supposed to go to end system 3, it should send to switch 2. And then switch 2 will send it to end system 3. But you can't have multiple choices. Okay, and if you don't have multiple choices, the side effect of that is that every packet I send will get to the destination in the same order. Because if I sent it first and there's only one path, then it's going to get there first. Now here's a make-believe topography of switches. So I've got here end system 5 in the cockpit going out to a switch, which goes to end system 4, end system 1, and another switch. And the other switch is sent to end system 3 and end system 2. So this is legal because there's only one way to get to any particular end system, right? In other words, to get to end system 1, I have to go through the first switch. To get to end system 4, I have to go through the first switch. To get to end system 3, I can't go directly from the first switch, so I'm going to send it from end system 5 to the first switch, who's going to send it to the second switch, who's then going to send it to either end system 3 or end system 2. There's only one way to get anywhere. It's just a visual way of seeing that. Now I added to the same picture a couple of VLs. So, and here I'm showing that VL1 I'm sending from end system 5, and the first switch is going to send it on both to end system 4 and to end system 1. Okay, let's say I have a bunch of VLs. So I've got VL1, which we saw in the previous slide, and I've added now VL2 in the back. Okay, so now if end system 5 said, now each VL, by the way, is only going to be sent by one end system. So VL1 is sent by end system 5. End system 4 can send VL 17 and 22. These numbers are being given out by the system architect when he designs the plane. So we know all the boxes on the plane. Each one of the boxes is given a certain number of VLs that it's allowed to transmit. And that way we don't duplicate, which obviously is going to simplify the work of the switch because he knows that each VL is only coming from one place. In other words, he knows which input port is supposed to have which VL, and if he doesn't get it, then that's an error condition. Okay, we talked about a bag. Now we'll find out that what a bag stands for is bandwidth allocation gap, right? And the purpose of the bag is to allocate bandwidth. It's giving, in other words, it tells each end system how much time do you get. So it's done through, it's not only, it's through each end system has a certain amount of time, but it's further divided that each VL within each end system gets a certain amount of time. So each kind of data that needs to be transmitted on the aircraft gets a certain number of milliseconds per second that it's allowed to transmit. So, right, and that means that if the bag is, say, 8 milliseconds, that VL is not allowed to go out more than every 8 milliseconds. In addition, the VL has a size, right? So if the size is, let's say, 300 bytes, including the headers, and we're talking about 100 megahertz Ethernet. So 100 megahertz means that you can send out 10 bytes per microsecond. So if you're sending 300 bytes, it's going to take you 30 microseconds to send this packet. Okay, so now I know that you're allowed, and if your VIA bag is 8, so every 8 milliseconds, you're going to take 30 microseconds. That tells me exactly how much time you're taking per, and now I'll look at the numbers, say, per second, so that if I have bags from all over the place, the numbers just get complicated. So I say, fine, I figure out how much you get per second, how much the next VL gets per second, how much the VL after that gets per second. I add them all up, and it better add up to less than a second. If not, I've done something wrong, and I have a choice of either reducing somebody's bag or reducing the amount of data they get to send, or reducing the number of end systems on a bus. Those are basically my three options. And between them, I make sure that my throughput never exceeds 100%. Obviously, when designing the plane, you would prefer that it not exceed 50% to give you room for adding stuff on later, which is certainly going to happen. Now, jitter is something that we have to take into account. Jitter means the fact that it takes a certain amount of time from the time that I want to transmit data to the time that the receiver gets the data. Now, there are different things that'll cause this delay. One of them has to do with my own device, right? On my end system, my radar has just detected something. Okay, well, I have a certain amount of processing to do in order to put that data in a format that I'm ready to transmit. And that processing takes time. So I have all kinds of internal things going on in my box that takes time, so that the data, by the time I transmit it even, is not 100% fresh. In addition, I'm transmitting it. Transmission takes time. Even at 100 megahertz, it is a finite amount of time that takes. Plus, it's going into a switch. The switch has processing to do. It finds out that the data came in. And mind you, this is actually an interesting thing in terms of timing. The switch itself is going to wait until the entire packet comes in before it tries to transmit it out of another packet. So let's say the packet takes 30 microseconds. It takes 30 microseconds to come in, and only after it's completely in can the switch send it out. So that's already a delay of 30 microseconds, right? Because the first bit came in 30 microseconds ago, and I'm only willing to send it when the last bit comes in. So I've waited 30 microseconds, and that's assuming the switch takes 0 processing time, which is not the case. The switch itself has to look at the packet and at the packet header, see what's the VL, look up a table that tells it this VL goes to this output port, or maybe these 3 output ports, and that all of that takes time. And then, having decided that it's going to these 3 output ports, it could be that another packet came in from a different device that also has to go out to one of those 3 output ports. Okay, well, it might have gotten there a tiny bit before, so it goes first, which means that I now have to wait for that packet to go out before I can send this one. So these are all things that cause delays between the transmission from one end system until the reception at a different end system. And we have to be aware of this. Okay, so now let's look at different ways that we can transmit devices based on their bag. So now I've taken it as an example 3 VLs. One of them is called T, and it has to go out every 2 milliseconds. One of them is called F, it's got to go out every 4 milliseconds, and one of them is called E, it's got to go out every 8 milliseconds. Right? So it doesn't mean that the T information is more important. I don't know exactly what important means. It means that the T information is more time critical. I need it now. So I want it to be sent out more frequently. Okay, so now I have 3 different ways that I can transmit these things, and all 3 of them are completely legal. All 3 of them are allowed by the spec. All 3 of them meet the requirements. And the requirements are that T goes at every 2 milliseconds, F every 4, and E every 8. And yet there are huge differences between them. The first is the simplest way of doing it, saying at time 0, I send everything. And then I'll send them according to their bags. So at time 0, I send T, F, and E. And then because T is sent every 2 milliseconds, at time 2, I'm going to send T. F is sent every 4, so I'm going to send F at time 4. Of course, I have to send T as well, because 4 is a multiple of 2. And then at 8, it's going to look the same as 0. So I'll start again with the TFE and so on. 8 is in all 3 cases the same as 0. Okay. The second method, I'll say, you know what? I don't want to send all three of them at time 0, because then at time 0, I've got too much going on, right? F has to wait for T to go out. E has to wait for F to go out. Why should I do that? Let me start all three of them in different time slots. So that's what the second column does. It says send T in time slot 0, F in time slot 1, and E in time slot 2, and then continue with all the rest. And it's a much, much cleaner method. In fact, here, the only time that you've got two different packets in the same time slot is at time slot 2. But it turns out I can do even better than this. And that's the third column. And the third column says, yeah, I want to start them all in different columns, but let's see if I can do it without any clashes. So I'll start T, the most frequent one, at time 0. Then the next most frequent one, I'll start at time 1. But I'm going to skip time 2 because I see that I've got an open slot in time 3. And then I'm still meeting all of my requirements, right? T is still going out every second one. F is going out twice in every 8 milliseconds. And E is going out once, and there's not a single collision. Now, obviously, I was only able to get away with this because I arbitrarily chose 3 VLs. There are going to be many more on an aircraft. So I probably won't be able to have only one VL per time slot. But clearly, I can minimize the number of VLs per time slot by having a more clever algorithm. Now, this is not anything that's written in the spec. This is something which the implementation has to handle. Okay, now here, this is a graph that's taken straight out of the specification. And it shows you some of what has to go on in the end system in order to process a packet. So here at the transmission side, I noted this is a bag. So I'm only looking now at a single VL, a single piece of data. Let's say this is transmitting altitude. So I transmitted every bag. A bag could be a millisecond, it could be 16 milliseconds, it could be 128 milliseconds. It doesn't really matter for purposes of this illustration. Point is that from the transmitter's point of view, he's going to send it out precisely every, let's say, for argument's sake, 16 milliseconds. So this is 16. This is time 0, time 16. This is time 32, time 48, and so on. Okay, so that's where he sent it. Because of jitter, right, the various reasons why things don't happen perfectly, they don't actually get to the receiver exactly at this time, right? They spend time in the transmitter processing, they spend time in the switch processing, and by the time it gets to the receiver, it's been delayed. Okay, that's okay. And remember, there's dual redundancy. So it was sent out both on A and on B simultaneously. Dual redundancy means different things in different specifications. In some, it means you always send it out on the primary bus, and if you have a problem, you'll send it out on the secondary bus. That's the most common way of doing it. AFDX chose differently. They chose to send everything out on both buses simultaneously and let the receiver throw one of them out. Okay, so based on what? So it got to the receiver on the A, got to the receiver here. The B got hung up somewhere and was pushed off a lot. Okay, so the receiver only has A to work with at this point, so it checks that A is okay, that there are no errors in it. And having checked that there are no errors in it, it says, okay, I got it. I've got the first packet sent by end system A. For the first packet of VL, whatever it was, of the altitude, came in, and I'm now going to accept it and send it up to my user. Okay, in the meantime, A sends out the next packet. B is still hung up over here, so A2 comes in. Okay, well, A2 comes in, we check for that everything is okay, and we say, okay, let's take that. Following that, B1 comes in. Okay, so now what do I do? So what I do is I say, well, I already got A1. I don't need B1. I can throw that out. I've already gotten this one. Then after that, B2 comes in. So well, I've gotten A2, so I don't need B2. So I throw that out also. And then I wait for A3. So A3 comes in, and I accept it. And then comes B99 because there's a bug in B, and I throw that out also. And we'll see in a second how do I know that A1 is the same packet as B1? How do I know that the intent is to be this same packet and that I already got it? Okay, right now let's go to another notion of a sub-VL, which is namely, we said that the maximum amount of time we give to a VL is 128 milliseconds. Now, theoretically, I could have data that I don't really need every 128 milliseconds. Right, among the data that's sent frequently is the time. And the time usually is sent to the nearest second. So it doesn't really do me a lot of good to get it every 128 milliseconds, which will end up coming in roughly 8 times a second. And it's not going to change 7 out of those 8 times. It's not too interesting. So what the spec says is, listen, what is the purpose of a VL really? The purpose of it is to give you a time slot. And because we want to know exactly how much time you're going to take up. Okay, well, that's your time slot. What you do with it is really your own business. So once you've determined that a VL has a certain time slot, I can say, you know what, I've got 4 different kinds of data that I want to send in this time slot. And that way, I'm still only going to send a packet once every 128 milliseconds. But if I have 4 different packets, then I'll send one of them at time 0, a different one at 128, a different one at 256, and onward, so that each one actually is going out really roughly every half a second, or technically every 512 milliseconds. So I'm allowed to do that. I'm allowed to share my slot among multiple sub-addresses. Turns out I'm allowed to share it with up to 4 sub-VLs. And let's say my slot comes up and I don't have anything to send, right? Because this is more likely to come up in the case of sending a file than in the case of sending an engineering unit. Because a file, sometimes I have a file to send and sometimes I don't. So I told the architect of the plane, listen, I occasionally have a file to send. If I want to send the file, I'm going to need to send 1,000 bytes every 128 milliseconds. But if I don't need to send the file, I don't. So he's going to assign me 1,000 bytes every 128 milliseconds for this file, for this VL. And I may not use it all the time. If I don't use it, then I just don't transmit. And that's perfectly fine, and it lowers the amount of work that the switches have to do, which is fine. Now, we talked earlier about sampling data versus queuing data. Oh, I thought it was 453. It's actually 653. That distinguishes between these 2 types of data. And the sampling data is where the format of each packet is the same, right? And typically that's for engineering data. Like I said, altitude, latitude, longitude. So altitude is going to be in byte 0, latitude in byte 4, longitude in byte 8, and that's always going to be the format of the packet. The contents are going to be different because as I go up and down, the altitude is different. As I travel, my latitude and longitude may change. One of them almost certainly. And so the packets are all the same. Now, the nature of this data is that old data is not of much interest to me. Now, let's say I'm looking at altitude. And 5 packets came in, and I, as the receiver, am busy doing other things, and I just didn't look at them. Now I want to look at them. What do I want to look at? Do I want to look at all 5 packets? The answer is no. I really only care about the last packet, because the last packet is the altitude that I'm at now. The previous packets are the altitude that I was at 128 milliseconds ago. I don't really care where I was at then. I care where I'm at now. So for my part, I'm happy to throw away any data that I didn't get around to look at. Obviously, if I didn't get around to it, it's because I don't think it's that important. I thought my other processing was more important. And so I'm happy to get rid of it. Queuing data, on the other hand, are things like files or databases or stuff like that. Maps could be. And there, it's somewhat different. The data tends to be larger. It tends to look different each time it gets sent. And if I miss data, I want it, right? And as if I'm putting together a file and I haven't been able to process it and another 3 packets came in, I don't want to practice I don't want to look at the last one that came in. I want all of them in the proper order so that I can rebuild the file as it was when it was sent out. Right, video data would be an example of this. And therefore, I want to have buffers, right? So that if I can't always get to it in time, I would like my receiver to hang on to all of the old data until I get to it, and then it'll give me all of the old data. Whereas in sampling, I didn't need it to do that. I didn't care if it had any buffers. It needed 1 buffer, obviously, but I didn't care if it had more than that. So that's the major difference between sampling and queuing. Now, a sequence number is going to explain how I know whether I got a packet in or not. At the end of every single VL, there's a sequence number. It's a byte with a number between 1 and 255. And every time I get a new packet, a new packet from that same VL, I expect it to be 1 higher. Now the same number is going out on A and on B, right? So if the number is a 1 and I got it on A, and then I get in packet from B with a 1 in it, I know I've already gotten that packet. And the rule says that I expect the next packet to be 1 greater than the previous packet in the ideal. And if it's not ideal, then all right, 2 greater I might be willing to buy. Because sometimes packets get lost and I have to allow for that. But more than 2 greater, I'm assuming that something went bad on the transmitter side. It wasn't the communication problem, it was a transmitter problem, and therefore I'm going to ignore it. So knowing about the sequence number, I can now understand, actually, let's go back to the previous slide with the bags. And now I understand that this 1, that's the sequence number. So when I got sequence number 1 on bus A, and then later on I got sequence number 2 on bus A, I accepted it because that's what I want. I'm expecting that. But then on bus B, I got a 1. I said, I don't want a 1. I'm already up to 2. So I throw it out. Then I say, I see the 2. Well, I don't want a 2 either. I've already got a 2. Then I see a 3. 3 is what I'm looking for. Then when this garbage 99 comes in, I say, that's garbage. It's supposed to be a 4. If it's a 5, I may buy it because, I'll assume that 1 packet got lost. But that's it. And therefore, I know when a bad packet comes in, and I know when a redundant packet comes in. Okay, we talked about dual redundancy. Now, graphically, I'll show you that the idea is that when an end system transmits, it never transmits on only 1 wire. There are always 2 Ethernet ports attached to the end system, and one of them is attached to the A network, and the A network means usually it's a switch, right? Everybody's going to be attached to a switch, and then the switch might be attached to another switch, or it might be attached to other end systems. So the network I'm just leaving as a blank, but the idea is that somehow through this network, it can get connected to the end system that needs its data. Now, within the specification, there is the ability to say that for particular messages, if I don't want to use redundancy, I don't have to. So I'll send them out only on A or only on B. Okay, so now that we know about serial numbers, we know that if a end system breaks and it sends garbage, I have a way of knowing about it. So here again, I show A1 comes in. It's the same picture, really. And I accepted A1, and then A2 comes in, I accepted A2. And now B9 comes in, right? Well, B1 came in, but I threw it out because I already had taken a 1. Then 9 comes in, and I throw it out because I'm up to 2. I need a 3 now. So B, for some reason, one of the switches on bus B is gone crazy. And all he's doing now is sending B9 a million times. Okay, well, it's going to do a limited amount of damage because I'm going to get my stuff on A. So I'll get A3 and accept it, and I'll get A4 and accept it, and I'm going to keep on ignoring B9. I'm only going to get B9 when I get A7 or A8. Then I'll say, all right, well, maybe the B9 is okay. I'm not smart enough to remember that I already saw 6 other B9s and had to throw them out. So I will get a bad packet occasionally, but most of the time, there's 250 of the, over 250 out of 256 packets, I'm going to not take a garbage packet. So that makes things a lot safer. Okay, now the reason that we need redundancy, I showed before how redundancy doesn't mess me up, that I'm not going to take both packets. But why do I want the redundancy? And that's pretty easy to explain. Again, I start out with A1 comes in, and A2 comes in, and I accept it, and then the B1 and the B2 I throw out because I don't need them. And in this case, the B3 came in before the A3. So I'm going to take it from B. So that gives me a minor advantage in that I get things faster, right? Whichever bus is faster is the one I'm going to get. So the dual redundancy picks me up a little bit of efficiency. But that's not its real advantage. Its real advantage is that in this, you see here, there is no A4. A4 got lost. I don't know if it got lost in the transmitter end system or if it got lost in one of the switches, but it's gone. But I don't care because I got B4. And then if it comes back, so I'll eventually use the A. And then if something gets lost in B. So I've increased my chances by way more than 2, because it's true, I went from 1 bus to 2 buses. But since the likelihood of an error on either of them is very small, the likelihood of an error on both of them is vanishingly small. And therefore, dual redundancy really picks me up a great deal of power. Now, if I have a super, super sensitive bus, I can have quad redundancy as well. I use A, B, C, and D. And the same mechanism is going to work. Okay, so to summarize, AFDX started out with Ethernet, right? It takes advantage of all the Ethernet standard protocols, hardware. That was their starting point. Then it added real time by using bags, by dividing the network into logical data units called virtual links, and assigning each one of those data units a certain amount of time that is allowed to transmit per second. The virtual link is used to determine the path, which switches it's allowed to go through, and there's only one path that it's allowed to go through. By having dual redundancy, we don't lose packets. And the method for both implementing dual redundancy and implementing all kinds of checks for different kinds of errors is the use of a sequence number. Okay, so now I hope you're all much more familiar with what AFDX does, pretty much in the theoretical end of things. Now we're going to move to the more practical end of things. I'm going to talk, now I'm going to use up until now, everything I've said has been completely generic, has nothing to do with Excalibur. But in fact, Excalibur does have an AFDX card, and we've learned a great deal in the process of developing that card. And I'm now going to share with you some of the things that we have learned.
Meantime, does anybody have any questions? Anybody? Okay. Proceed.
Onward. Okay, here's a picture of of our card, and as you can see, there's a base card, and then there are 2 modules. And the modules have nothing to do with AFDX. We'll get to them in a little while. So what does the card do? So it has actually two dual redundant transmitters modules and two dual redundant receive modules, meaning that you can act, right, an end system needs to be one transmitter and one receiver. So you can simulate two completely independent end systems using this card. You can actually simulate more than that by using software tricks, but you can actually simulate two end systems in terms of having a bus A and a bus B coming out and being connected to one place, and another physical wire, bus A and bus B, being connected to other switches, for example. In addition to supporting two complete end system interfaces, we can also support, using the two additional modules, other specifications. So ARINC-429 and ARINC-825, which is CAN Bus, are an example of things that might very well work together with AFDX. Although we also have other things like MIL1553 and serial and discretes and a whole bunch of other modules that could be useful. And the interface also, we support ARINC. Chaim, you may want to check the mutes. Meaning that we time tag on receive, we time tag all messages that come in. And there are two kinds of time tags that can be used. One of them is after reset, we start from 0 and then keep counting up. And the other is an IRIG-based time tag. IRIG is taken from a satellite, so you need to have a receiver to get the IRIG. And then we'll attach to each message the IRIG time. Now, IRIG time itself only gives you to the near, let's see, this is accuracy to the nearest second. No, precision to the nearest second. We add to that our own microsecond counter. So every second that comes in, we start counting microseconds. So that gives you a accuracy and precision to the nearest microsecond. Okay, now in terms of, so we have to allow for transmission and for reception. Turns out there's very little connection between transmission and reception, right? If I have something to transmit, I transmit it. If somebody else sent something to me, I have to receive it. There's no real interaction there, which is another difference between ARINC and Ethernet, in which there tends to be more of interaction. For example, ARPs and pings, which are used in Ethernet all the time and need to cooperate, right? I send something to you and you have to respond to me. So it's kind of a handshake. There's not a lot of handshaking going on in AFDX.
Dave.
So we'll discuss transmission and reception separately. And there are two different modes that are used in transmission, what we call bag transmission and busless transmission. And there are three modes used in reception, which we'll get to.
Somebody
so the first of the, yeah.
Somebody wants to know if IRIG input and output are both supported.
I don't think we do output on this card.
Okay.
Right. I know on a bunch of our cards, what we do have is a simulated IRIG, where we'll give you the IRIG time tag even if you don't give us the input, but obviously you'll have to tell us what time to start with, or else we'll just start with time 0. But yeah, no, that we're using it for our time tag, so we just get it in. Okay, in bag transmit mode, so this kind of simulates what's going on an airplane more closely, because, as we said, the system architect assigns, tells you which VLs you're entitled to use, how often you're entitled to send them out, how large they're permitted to be, and that's what you do. You send those. Now on the card, you can simulate 100 different VLs, which theoretically means you're simulating a dozen different end systems, right? Because I said each end system gets its VLs, and VLs are assigned only to a single end system. So each, let's say for argument's sake that your average end system has 10 VLs. Well, you can arrange your packets in such a way that they look like they're coming from 10 different systems, even though they're coming from one. So it depends how your lab is set up, if this is a useful thing for you or not. But we allow you to set up virtual links. We can allow you to set up sub-virtual links. And then you hit start. And what you've got is a list of things. This one I need to send out every 32 milliseconds. This one I need to send every 64. These I want to send out every 8. And then you hit start, and you say, basically, you tell us you handle the timing. It has to follow the rules that I gave you. These are the bags, these are the VLs, these are the sizes. But having given you the rules, the actual order sequence, that's up to the board. And the board arranges the load balancing and round robin transmission and fragment processing. We'll get to what those things are. And so we take all of that timing issues off of the user's back. So we saw before, remember we had a similar slide and I had three different columns of ways you could do it. So I got rid of one of them here. But I kept the first and the third. So the first is the not very efficient way of doing it, in which you send out all of the VLs at time 0. And then from there, you just keep sending them out according to their schedules. The second way, which I call load balancing, is figuring out what's the most efficient place to start each one of these VLs so that we don't have more VLs than we need to at any time slot. Now, I arranged the example in such a way that we only have one in each time slot. That meant it may not always be possible, but definitely the load balancing will give you the most efficient way of doing it, which is much, much better than just doing it, all of them starting at time 0. So that's something that the card takes off of the user's back. Round robin happens when you have sub-VLs. So if you define sub-VLs, then what we'll do is we will take the VL slot and divide it among the sub-VLs. So here, you've defined VL1 with a bag of 2 milliseconds, but it has 2 sub-VLs, which means that it has to go out every 2 milliseconds, but you can split those among the 1 and 2. So at time 0, we're sending out the first sub-VL, and at time 2, we're sending out the second. Then at time 4, we go back to the first, and then at time 6, back to the second. That's the round robin idea. And again, we handle that. All the user has to do is define how many sub-VLs there are in this VL. Fragment processing also is something that the board can handle, and a queuing message you're allowed to have up to 8K bytes, but there's no way to send that on the underlying Ethernet, because the underlying Ethernet can only have 1514 bytes. And that includes the sequence number, by the way, and all the headers. So in terms of actual data, it's really more like 1471 bytes. So if you want to send an 8K packet, then it has to be split into fragments. And each fragment goes out during your bag slot. And again, the board handles all of that. So that's the first mode. And the advantage of the first mode is A, it's similar to what happens on an airplane. And B, it takes a lot of the work off of the user. On the other hand, that's not what everybody always wants, because the card is used for testing. And when you're testing things, you don't necessarily want to be exactly like an airplane. And you don't necessarily want the work to be done by somebody else. The reason for this is sometimes you want to control exactly what the test is doing. And if you want control, then you want to decide what the order of events is going to be, what the order that the VLs are going to be transmitted is. And if we decide and we do the load balancing, you don't have control over that. We decide when they go out. Whereas we give you now a different mode, a bus list mode, in which the user gets full control over the order of every single packet that goes out and the timing. So again, the user defines the VLs and the sub-VLs, but Now, instead of giving us a bag and letting us decide how to arrange it, the user says, no, this is the order that you're going to send them out, and this is the time between transmissions. So you, effectively, you're taking away the need for a bag, which means that you can do a lot of illegal stuff, right? You know, you can have something transmitting not every 4 milliseconds, but it's under your control. So you can do what you want. And if you want to do something illegal to see how your end system handles it, that's perfectly fine. We'll still handle the round robin and the fragmentation, because that's something that's very difficult for a user to do, and because it's totally predictable what we're going to do. So we're doing the work for you, but we're not making any decisions for you. You make all the decisions, we just carry out the implementation. Okay, so those are the two standard methods of transmission, but there's a third method, and the third method is used for something else entirely. It's really going to be used when you've already got a working system, and let's say you did some flight testing and monitoring on the system, and you would now like to review what went on. So, and specifically, there are two things you might want to be checking. First is, let's say something happened on the flight. 10 minutes into the flight, some lead went off, and you don't know why, and you want to find out why. So you want to reproduce the same situation in the lab, where you can now look at all the various devices and figure out what caused the problem. Okay, how do you reproduce a situation? So what we offer is that when you monitored the things on the plane, we kept a file, or the application kept the file, of everything that came in, all the data that came in, all the packets, including all time tag. So we know the exact data that went over the bus, and we know exact order that it went over the bus, and the timing. Now you feed that into our data reconstructor mode of transmission, and we will transmit out exactly what was received in the last time. So now if you, and we'll do it for either everything, or you can say, no, do it for all the messages other than these particular VLs. And if you do that, then you can now attach the box that had the problem to our card. As far as the box is concerned, it's getting in the data that it got, it's getting the same data that it got on the aircraft, therefore reproducing the same environment that it had on the aircraft. And with any luck at all, it'll reproduce the same light that it did. And now we'll be able to narrow down what's going on. We can put debug into that box and see what's bothering it. In this case, we do a lot less. All we're trying to do is reconstruct what happened on the plane, so we don't know about fragments, we don't know about all of those other things don't matter anymore, because the fragmentation was already done before, and we received the fragments. So we're going to just send them out exactly as we got them in. Okay, so that's that finishes up the 3 transmit modes. Now we've got 2 receive modes as well. And again, the reason is that there are different things that you might want to do when you're receiving. One is you might want to receive the same way an end system receives on the aircraft. Now what that means is that each VL has its own buffers. You define which VLs you're expecting to receive. And then as the data comes in, each VL is going to go to its own buffer. And so what your application will do is it'll have defined all of these VLs. It knows that this VL contains altitude, this one contains latitude, this one contains time. And whenever it's looking for time data, it's going to look at that buffer. When it's looking for altitude data, it'll look for the altitude buffer, and so on. So now the board does rebuild fragments into messages, and will only report to the user that it has a message when all the fragments have come in and the message is complete, because there's not much you can do with a partial message. There are also various errors that we'll detect. If you define the VL is supposed to come in every 8 milliseconds, and it came in after 10 milliseconds, we'll tell you this one was late. And we'll do all kinds of other error checks, parity checks, data integrity checks. Is the sequence number correct? there's a lot of things that we're able to check. We will not store redundant packets because that's the waste of time. If you want us to, I think we will actually, but the standard mechanism is not to do that. So this is the method that you use for testing your end system, if that's what you're. Let's say you built an end system, or you're building one, and you want to handle the communications aspect of it. This is the best method for doing that. On the other hand, if you are putting together an aircraft, let's say your Airbus, and you've got in a whole bunch of your subcontractors have given you their equipment, and now you want to check it out. So then you're not really looking at it from the perspective of an end system. You're looking at it from the perspective of the entire system. So here you might be better off with a sequential monitor. Sequential monitor does is it says every packet that comes in, it time stamps the packet, puts it into a buffer, and it's ready for you to read. And you can read every single message that came in the order that it came in, not divided by VL, but all of them in the same place. If a fragment comes in, we'll give it to you at the time that it came in. We won't rebuild it, but we will tell you that it's part of a fragment. Of course, you have the header in the information, so you can look at the fragment information if you're so inclined. But even before that, we have a status bit that says this is a fragment. We also do all kinds of checks if the packet was a legitimate packet. If there's a problem with the packet, we'll throw out redundant packets if you don't want them, because typically they're not meant to be actually received by the user in AFDX. Okay, that pretty much covers AFDX. So I'll just talk for a minute about the other modules, because there's room for 2 modules on the card, as we saw. And we've got a whole bunch of different modules, including, but not exclusively, ARINC-429, ARINC-708, serial, discretes, and MIL 1553, which is less likely to be used together with AFDX, which is a civilian spec, whereas MIL 1553 is, of course, a military spec. But we've also got a CAN bus. Actually, let's not talk about CAN bus here. And so these modules are also available with the card. As I mentioned before, we support ARINC timing. We've got just a standard timer on the board so that if you want to know when 10 seconds has elapsed, it'll tell you, or 10 microseconds for that matter. Interrupts, polling, extended temperature conformal coding, all kinds of fun things. Okay, that's it for AFDX. Thanks for listening. And if there are any questions, this would be an excellent time to ask them, either by unmuting or by sending Chaim a message. And if you think of any questions later on, you've got our email, so please feel free to do that. I'd also like to point out that we're always happy to be asked questions, and if you're starting a new project and you need some information about the best way to go about it from a communications point of view, we're happy to help, both because we're just very generous people with our time, and because it gives us an insight into the kinds of projects that our customers have, and that's great information for us because it helps us improve our product. Thank you very much. Okay.
Are we
So
doing
I
CAN
guess,
bus?
yeah, I got CAN bus. It might be time for a couple of minute break just because this is a lot of material.
Okay. Everybody up for CAN bus? Or if you are joining us tomorrow for ARINC-429, we could do it then. Does anybody have any preferences? Okay, so I guess we'll do CAN bus now.
I guess so. Let's see.
Somebody's asking if we do ARINC-818. I'm sorry to say that no, we don't do all protocols, and ARINC-818 is not one of them. So if
we do get asked it a lot, so we do think about it a lot. Maybe one day.
There we go.
Okay. CAN Bus is also a civilian avionics spec. Actually, going back, CAN ARINC-825 is a civilian avionics spec. It is based on CAN Bus, which was developed by Bosch a very long time ago for cars. It was, now Bosch updated the car spec in 1991, but the ARINC spec was only released in 2010. We're now up to ARINC-825.4, which was just released like a year or so ago. The major difference is that 0.4 deals with a faster speed for CAN Bus. It's not yet in a great many implementations, so I'm going to be focusing on the more standard low speed, which gives you up to 8 bytes per word. Okay, so what is CAN Bus for? And really the question I want to answer at the very beginning is why was AFDX and CAN Bus, were AFDX and CAN Bus both developed at roughly the same time and both used for the same kind of thing? They're both used for civilian aircraft. And the simple answer is that their uses are somewhat different. CAN 825 is used for very near systems. In fact, at its highest speed of the standard, which is a megahertz, it's only allowed to have up to 50 meters of cable, which when you're talking about a large aircraft is not a lot. I remember that the buses tend to bob and weave and turn, so 50 meters isn't going to get you very far. In addition, it only allows very small bits of data, up to 8 bytes, which means that it's used for, it's going to be used for smoke detectors. It's going to be used on galleys. It can certainly be used for things like landing gear. But these are all things that don't have a lot of data associated with them. Whereas AFDX, based on Ethernet, can handle large amounts of data, right? It's 1,500 bytes at a time. And it can go for hundreds of meters because it's you've got a bunch of switches in the middle, and there's really no limitations over there. So it turns out that if you've got localized short amounts of data, you're going to use CAN Bus. And if you've got large data, you're going to use AFDX. I asked a fellow from Boeing once how to make the decision, and he says really not that complicated. A CAN Bus link costs about $2, and AFDX costs about $2,000. So they use CAN Bus whenever they can. Okay, now, because it's the same plane, so if you use some on CAN Bus and some on AFDX, you need some way of interacting between these two things. And that's often done through what's called a gateway. So you'll have a CAN Bus, which will be connected to, let's say, 20 different devices in a localized area of the wing. And you'll have a gateway, which is one of the devices on the CAN Bus, and that gateway on the other side will be connected to an end system of an AFDX system. So through the gateway, all the data that was developed or that was received by all of those 20 or 50 devices on the CAN Bus can now be sent to the cockpit via AFDX. So you'll have the short from the gateway, you'll be attached to a relatively small localized bus that has maybe 50 different things on it. And then you'll have a single wire going from the gateway to the cockpit, bringing all of the data at the same time. So that way there is a connection, and this connection is brought out in the spec, both in the AFDX spec and in the CAN Bus spec, well, in the ARINC-825 spec. They talk about the use of gateways to share data between the two buses. You can also share data between different CAN buses. So you'll have one CAN bus connected to these 25 sensors and another CAN bus connected to another 25 sensors. And if two of the sensors need to talk to each other, then they can be connected to each other. Okay, so now that we know what a CAN bus is used for, what does it actually look like? I didn't do this in Ethernet because it turns out that Ethernet is a mess. AFDX looks like Ethernet, and nobody cares what Ethernet looks like because you really need specialized equipment to read a packet. However, if you put an oscilloscope on a CAN bus, you can actually understand it. In fact, it's one of the simpler buses because it's serial. So here, first of all, it's a differential signal. Differential signal means, and I'm down here, let's give me a little color here. Change pen color. Let's go with red today. Well, probably not actually red, but I don't know the difference. Okay, so I've got here is the CAN low, and here is the CAN high. Means there are two wires. That's what a differential signal means, that there are actually two wires there. Now, this is not dual redundant because you need both wires in order to get the signal across. And one is always the complement of the other. So that here, high, let's say you have a 0 is the first bit you want to send. The high is going to be high for a 0. The low is going to be low for a 0. For a 1, the bus called CAN high is going to be low, and for low, it's going to be high. This tells you that CAN bus was developed by hardware engineers who have a tendency to do everything backwards. Certainly, that's been my experience. Anyway, just a word about differential signals. When you have a differential signal, so then this, let's say, is 3 volts, and this is minus 3 volts, and the distance between them is 6 volts. Here, the distance between them is 0 volts. So by looking at the two signals, I have a very easy way of telling what's a 1 from a 0. If I only had one of them, then I would have to say, all right, 3 volts is a 0. And 0 volts is a 1, which sounds simple, but the reality is, when I say 3 volts, what I mean is 3 volts relative to ground. Now, of course, I'm on an airplane. There is no ground. So each device kind of defines ground for itself. And it turns out that what one looks at as ground, the other one might think is 2.5 volts. So it's not the safest way in the world to tell a signal. Whereas if I'm looking at the distance between them and I say, is it 6 or is it 0? That's very easy to tell. Because it's not relative to ground, it's just relative to each other. So differential signals are just cleaner, easier signals not to make mistakes with. Okay, so now going through the fields, it doesn't, these are the various fields. I go through them briefly because we're going to see them more in detail later. And what you have first is what's called an arbitration field, which is also called the identifier. And we'll talk about what an identifier is, but what it's for is to tell you what kind of data is following. Then you have a control field, which tells you how many bytes are following. Then you've got the actual bytes, which can be up to 8 bytes. Then you've got a CRC, which the hardware handles. The software doesn't know about it. But the CRC is generated by the hardware and it's read by the hardware so that if there's an error in the data, we know about it. And then you've got some bits that tell you that you're done. This is now the end of the frame. Okay, so now let's look at it in a way that people can understand rather than on an oscilloscope. And here you've got the 29-bit CAN identifier is this field. Skipping the detailed fields, we'll go again. You've got the control field, which contains a number from 0 to 8, telling you how many bytes you're going to have. Then you've got 0 to 8 bytes, and then the CRC. So those are the major fields. Now, from a user's point of view, he doesn't care about most of these things. The user cares about three things: the identifier, the control, which is the number of bytes, and the actual bytes. Everything else is necessary for the hardware to know where's the beginning of a message, where's the end of a message, is it a legitimate message, or are there errors in it? But the user pretty much doesn't care about any of that. Now, the original CAN, the one developed by Bosch for cars, actually had an 11-bit identifier. CAN 825, or I call it CAN 825, it's really ARINC-825, which is the avionics instantiation of the CAN bus. So I tend to just call it CAN 825. It doesn't use the 11-bit identifiers. It will read a message that was sent by an older CAN bus, but no avionics device is going to produce such a label. And the reason for that is because a lot of the effort that went into putting together the ARINC-825 bus went into defining the identifier. Bosch didn't define anything. They just said this is an identifier, consider it an address. And so if you give everybody on the bus a different identifier, then they were happy. That was their intent. But 29 bits gives you the ability to have 500,000 different identifiers. You don't need 500,000 different devices on an airplane. It won't get off the ground. So they decided to use it for something that's a bit more meaningful. And this is, so this definition of the identifier is strictly out of ARINC-825. It was not in the Bosch original spec for cars. And it divides in the identifier into subfields. The top field is the kind of communication channel you're talking about. And as we divided the kinds of data that go out into basically 4 different categories, but there's room for expansion because there are 3 bits, so we could have really 8 categories if we wanted. But the 4 categories, the one that we use the most, of course, is the normal category. There's a thing called node service, which are housekeeping kind of things. You use that for stuff like uploading files, downloading files, and synchronizing the bus. And there's not, right, well, not the standard kind of data that goes over. And then you've got exceptions, which are very high priority messages and low priority messages. Like if you've got a file that you'd like to send, but as long as it gets here sometime in the next hour, I'm happy. So I don't want to take up time that's in use, but if I see an opening, then I'll throw it in. Okay, so that's the first field. The next field, and the other fields are mostly used for the normal channel. So the first field is the source FID. Source FID is what is the name of the box that is sending this data. And so flight control is an example, tail rotor, galley. These are examples of where the data is coming from. And if you know where the data is coming from, then that gives you an idea of whether you're interested in the data and what kind of data you're likely to get, right? So an inertial navigation system is likely to give you things like altitude, latitude, and longitude. It is less likely to give you information such as how hot is the oven. And the galley is the reverse. So we just did the source bit over here. Now we're up to, well, this is a reserved bit, so there's not much to talk about. A local bit tells you whether you're allowed to use a gateway or not, right? We saw before that CAN buses are often attached to gateways, which will lead onto an AFDX bus. But not all data is going to be interesting to the AFDX bus. And the data through the identifier is allowed to say about itself, I'm not interesting, don't pass me on. You've got a private bit, which is not particularly interesting, to be honest. It's used for special cases because data is defined within the spec as being a byte integer, a word integer, a floating point integer. There's various types of data that are defined. Occasionally, you'll have some manufacturer that has a need for a very specialized kind of data that doesn't meet any of the specs definitions. Obviously, if he's gonna send something that doesn't meet the definitions, he's gonna have to have a receiver somewhere who also knows about this. So this bit tells the receivers this is one of those kinds of data that is not well defined by the spec. And then you've got the data object code, which is the large field, which tells you what kind of data are we talking about. Are we talking about altitude or longitude or oven heat or number of liters of gas in the tank, etc. And that is the most important field for the receiver to use to understand what he's getting. And the last field is a redundancy channel identifier, 2 bits, which means that if you want to have dual redundancy on a CAN bus. So the CAN bus itself tells you that it's a good idea to have it, and it gives you these 2 bits so that if you're sending data on 4 different buses, they know which one they are. Now, typically they're going to know anyway because they're physically attached to it. But it turns out that there are cases in which it's useful to have this information. So that's the CAN identifier, and that pretty much is most of what defines CAN bus. The data itself is from 0 to 8 bytes, right? So you might have 0 bytes because just the very fact that you got a message from a device tells you something. Now, within those 8 bytes, you can have more than one engineering unit. You know, right? Latitude and longitude can be in the same message because each of them typically only needs 4 bytes. Now, CAN uses big endian format, which is the same format that Ethernet uses. That's mostly important if you're using a PC, for example, to connect to a CAN bus, and PCs use little endian format. Now, what is big and little endian format? Most people don't care, so I'll be brief. But let's say you've got a 16-bit number. So computers inherently work in bytes. 8-bit byte is the most natural form of information. Now, let's look at it this way. The number 10, right, in decimal. The 0 is the least significant bit. It means let's actually the number 12, just to make it more interesting. The 2 means 2. The 1 next to the 2 means 1 times 10, right? So it's the position that you're in tells you what your value is. The lowest position is the 1s, the next position is the 10s, and then the 100s. On computers, that's true of bytes. The position of the byte tells you its value. So the lowest byte is going to be whatever value it is. The next byte is going to be 256 times that value. So the question came up, if I've got a 16-bit value, so it's 2 bytes long, is it the first byte that's the most significant byte, or the second byte? Which byte is it that you multiply by 256? Well, because there are 2 possibilities, different companies chose 2 different ways of doing it. And the main companies at the early ages of computers were Motorola and Intel. Motorola decided that the first byte should be multiplied by 256, and the second byte, and there's address 0, you multiply by 256, and address 1, you don't. Intel, of course, decided the other way around. I may have gotten that backwards. In any event, because that continues till today, and Intel, which has a vast majority of the market of processors these days, uses little endian format. Ethernet decided to use big endian format. So it doesn't matter, but you have to know. And if you're using 2 systems together, then you're going to have to do some translation, which isn't difficult to do, but you got to do it. Okay, now in this case, the specification actually writes in it what kind of data you're supposed to send. So that if you're sending latitude, it tells you send it as an angle. Actually, no, it tells you to send it in radians. Right, angles can be done in a number of different ways. One way is degrees, minutes, seconds. Right, you're familiar with 90-degree angles, so that's a degree. Radians is another method of doing it. There's another method called semicircles. Mill Standard 1553 tends to use semicircles. ARINC-429 tends to use angles. CAN Bus uses radians. Acceleration, meters per second. Now, it's possible that this is going to be altered a little bit by different manufacturers. For example, no one at Boeing knows what a meter is. Airbus, they know what meters are. Boeing knows what feet are. Airbus knows what liters are. Boeing knows what gallons are. So these things happen. The spec was written mostly by Airbus, so it says meters, but don't be at all surprised if you're working with Boeing and they tell you don't bother. Okay, so your standard message type is the identifier that we defined before, and the important things to remember from that is that it identifies the source of the data and the type of the data. There are other messages. Here is an example of a periodic health message. And a periodic health message is sent usually once per second by each box on the aircraft. And its purpose is just to let some central computer who's monitoring this know how things are doing. So each CAN bus chip keeps track of certain things. Particularly what it keeps track of is how many errors it's had on receive, how many errors it had on transmit, how many errors it had. And all of this data comes together with in the health message. So the first thing you see in the health message is that there's a fixed value in the first whole bunch of bits, right? So there's, instead of having the just one value telling we used before, it was the type of equipment. Here I don't so much care about the type of equipment. I'm going to get that data later in the server, so I'll know who you are. And in fact, when you're talking about data such as altitude and latitude, I don't really care which particular box you are. I care what type of box you are. Are you a navigation, an INS, right? Are you a GPS? So that's, on a regular message, that's what I care about. On a health message, I don't care about that so much, but I care about physically, who are you? So that if I have, for example, 4 inertial navigation systems on the aircraft for redundancy purposes, on a standard data message, they're all the same. I don't have to distinguish them because they're all giving me the same kind of data, and that's what I care about. Am I getting the altitude or not? Whereas if I want to know if a box is healthy or not, what I care about is physically, are you the first, the second, the third, or the fourth? Because if one of you is going to be sick, I'm going to take you off the bus. And I'm not taking you off because you're an inertial navigation system. I'm taking you off because this particular box is not working. So the needs are different in a health message than they are in a standard data message, and therefore the identifier is different as well. So here, the kind of information I'm going to need is really who you are, which physical box you are. Now, in terms of the data, so that was the identifier we talked about. In terms of the data itself, so this data has also changed from version to version. So I'm giving you one of them. They're all roughly equivalent. And the tech and the rec are registers defined by Bosch in its definition of the CAN bus. And that tells you how many errors have been gathering up. And it turns out that whenever a CAN bus device gets a good message, the transmit error counter goes to 0. So if it's a non-zero value, you know that recently it hasn't had good messages. The same for the receive. Now, after you get a certain number of messages, a CAN bus turns itself off and it has to be reset. So in the health message, we tell you, has that happened and how many times? And then there is a 2 16-bit values telling you how many errors altogether have you had, because the tech and the rec only tell you about the most recent situation. Whereas these are going to tell you from the time you turned on the box in the morning, how many errors have there been. And based on this information, you can tell whether you've got a problem. Certainly, when you land, this is going to go into the maintenance log, and the engineers going over the plane are going to want to know which devices had problems, and maybe they would switch them out. Here are a couple of, now we had said at the very beginning that there are standard messages and there are special node service code messages. So these are the housekeeping kind of things, such as node ID service is a way of every box identifying itself, saying who he is. Synchronization service will tell everyone to, it's usually done by a broadcast, and will tell all of the boxes to reset their time tags so that they're all know when somebody sends out time, they all know what it means, instead of each having their own clock. Then there's upload and download, which is a way of moving the files around. And there's a bit control, which asks a device to perform a self-test. So whereas the health message tells us the health of the communications, right? Because they're all communication errors that those counters were all about. But the bit tells us if you're, whatever it is you do for a living, if you're a GPS, do you have good contact with the satellite? Might be something that the bit control service tells you. Or in fact, usually you want to have access with multiple satellites. So the kind of information you expect from a bit of a GPS is, yes, I am in good contact with 4 different satellites. Okay, so now that we know what a message is and what kind of data goes in a message, what's left is to understand how often does the message go out. And it turns out that the frequency that a message goes out is very much dependent on the kind of data that you're sending, right? So that sending the data such as the time, you really want to send roughly once per second because most clocks are accurate to the second. On the other hand, you might want to know fuel quantity being burnt in the engine 10 times a second. And you might want to know if there's a storm coming your way 20 times a second. So I'm making these numbers up, but you get the idea that different kinds of data is different in terms of time criticality. And that's what this chart is for. So the chart is divided into a major frame going down and minor frames going across. So these things get sent one line at a time, right? We're going to send first the first line and then the next line and onward. Now, in this case, I'm looking at the scheduling from the point of view of the engineer of the bus. Now, as I'm not looking from the point of view of a single device, like the engine, but rather all the devices together. Because the engineer's job, the architect of the system's job is to make sure that there's enough time for all the data that has to get transmitted. So the first thing he'll do is he'll say, all right, what are the most important messages? The messages that have to go out every single frame. And those are messages A0 through A7. And every frame, and what a frame is also, he's going to determine that. Let's say, for argument's sake, a frame is 100 milliseconds, which is a reasonable number. So he's going to say, okay, these 8 messages are so important that they're going out every 100 milliseconds. However, B is another device, and it doesn't have to go out every single time. What it's going to do is there are 2 kinds of B data. Well, B0 has 2 kinds of data, and they're going to switch off. So the first frame, one type of data go out. The second frame, a different kind of data is going to go out. B1 data only has 1 kind of data, but it's not any more important than the B0 data, and therefore it'll just skip every other frame. The C, I've got 4 different kinds that are going to switch off. C1, only 3 kinds, but so every 4th kind I'm going to just leave it alone, and so on. So this gives you a choice of how frequently you want to send data. So in this particular example, if I say that a minor frame is 100 milliseconds, these go out every 100 milliseconds. B0 sub 0 goes out every 200 milliseconds. C0 sub 0 goes out only every 400 milliseconds. So depending on how time critical the data is, using my schedule, I can now make it go out more and less. So I say, according to this, I've decided that a frame is 30 milliseconds. So that this is 30, this is 60, but the same concept. It really doesn't matter. Okay. Now I'm drilling down to a very low hardware level. Because it turns out, and this is something that comes up with all the various courses we give, and we well, we just had the Ethernet course, but 1553, 429, 1553 I gave 2 days ago, 429 I think we're doing tomorrow. All of them have different ways of sending a bit, of distinguishing between a 0 and a 1. And we saw here that CAN bus is one of the simpler ways. High is a 0, low is a 1, or on the redundant bus, it's the reverse. There's a problem with this method, which is namely that, let's say a single bit is a microsecond, right? There is such as, there are actually about 8 different speeds used in CAN bus. A microsecond is one of them, it's the fastest one. Okay, so then if this is high for a microsecond, I know I have a 0. If it's high for 5 microseconds, I know I have 5 zeros. The problem is, how do I know how long a microsecond is? It turns out that the way I know it is that I have an oscillator on my card, and the oscillator tells me. But oscillators turn out not to be perfect. So to an oscillator, 0.999 of a microsecond is good enough. 1.02 of a microsecond, that's probably good enough too. Now that's okay, as long as all of my oscillators on the plane make the same decision. But of course they don't. So if you have one of them that's a little bit fast and one of them that's a little bit slow, on a single bit it's not going to matter that much because it's going to be fairly close. But the more bits that I put next to each other, I'm going to be multiplying that error each time. And so if I have too many bits in a row, let's say I've got 100 bits in a row, so one of them might think, one of my oscillators thinks that that's 101 microseconds, and the other one thinks that it's 99 microseconds. How many bits do I have? 99, 100, or 101? So it's a bad idea never to switch, to have just a straight line. Now here, when I see this line is going down. So in addition to telling me that the bit value has changed from a 0 to a 1, it tells me something else also. It tells me that right here is the end of one bit and the beginning of another bit. So if my oscillator has been off by a little bit, and you know, first I was on target, both of us knew it was the beginning, and then you thought that it was a little bit in, and I thought that I'm a little bit more in, I lose track of where is the beginning of each bit. But if once I change something, then I snap back and I know, okay, now I know I'm between bits. So what CAN bus decided is that if you got more than 5 contiguous bits that are the same, I'm going to stuff in another a 1. So that really, if I have 10 zeros that I want to send in a row, what's going to go out on the bus is 5 zeros, a 1, another 5 zeros. Now, the receiver knows this. So when the receiver sees 5 zeros and a 1, it's going to throw out the 1 because it knows that this one is only there to synchronize me. And it's not really a data bit. So as long as both sides are in agreement how that's going to work, we're fine. Of course, if you have 5 ones in a row, then I'm going to throw in a 0. And that way, I get past the major problem with this method of encoding, which is the problem of oscillators not being perfect. Turns out that 429 and 1553 use totally different methods, and they don't need this. Okay, next question is arbitration. And again, this is a question that we have to ask for every single bus. How do I make sure that I don't have multiple devices transmitting simultaneously and making them crash on the bus? So in Ethernet, it's very simple, really, because nobody is connected directly to, you never have multiple transmitters on a bus. My device is connected by wire to a switch. So I'm the only one who can transmit. I mean, it's two directional, but I'm the only one who's transmitting to the bus here, to the switch. There might be 10 other devices transmitted to the same switch, but they're transmitting to different ports. And each port on the switch has a buffer associated with it. So that if the switch then has to take data from 2 different ports and transmit them out of the same port, it just said, okay, fine. One of you sit tight in your buffer. I'm going to transmit the one who got here first. You'll wait, and then I'll transmit you. So there's never an issue of having more than one thing going out on a wire simultaneously. However, in CAN bus, it doesn't work that way. There are no switches in CAN bus. Everybody's connected to the same bus. And all of them can transmit whenever they feel like it. I mean, there's a schedule in terms of how frequently they're allowed to transmit. That's what we saw in the minor frame thing. But that just says that if they transmit, they now have to wait a certain amount of time before they transmit again. But it doesn't coordinate them with anybody else. Okay, so the way that they handle this, and this is different on every bus, the way they handle it is that in the hardware level, if let's say they do start transmitting. Basically, what they said is, okay, go for it. Everybody can transmit whenever they want. Okay, so now how do we stop them from crashing into each other? Well, physically, the way it works is that if they do start transmitting simultaneously, so then there are three possibilities. Either they're both transmitting a 1, or they're both transmitting a 0, or one is transmitting a 1 and the other is transmitting a 0. And of course, either one could be either. So it turns out that, first of all, every bus, while he's transmitting, is also looking at what's on the bus. Now, if they both transmit a 1, then of course he's going to see a 1 on the bus, and he's going to say, well, that's good. If they're both transmitting a 0, he's going to see a 0 on the bus, and he's again going to say that's good. And in either case, he's going to continue transmitting the next bit. However, if one transmits a 1 and the other one transmits a 0, when they read it, both of them are going to read back a 0. So the one who transmitted a 0 and reads back a 0 is happy. The one who transmits a 1 and reads back a 0 says, whoops, there's somebody else on this bus and he's transmitting a 0. I'm going to let him go first. And so he's going to stop transmitting at this point. Okay, effectively what that means is that an identifier that has more, identifier is the first part of a message to be transmitted. And so an identifier that has more zeros is always going to go first. Because one of them that has, as soon as one of them gets a 1 and the other one is a 0, the one that has the 1 drops out. So the one with more zeros is going to go first, which effectively means that if I look at an identifier, at two different identifiers, I look, which is the lower number? And the lower number is the one that has the higher priority. So when a system architect designs the system, he's also going to assign lower identifiers to more time-critical systems. Okay, now in terms of connection to the bus, again, different buses use different methodology. Ethernet uses a switch is the way you connect to a bus. In CAN bus, you actually just kind of twist your wire onto the bus. Now, actually, obviously, there are smarter ways of doing it. And the spec defines resistors, termination resistors. The resistors make signals cleaner. And terminators make systems cleaner. So this is just physically the way that you're going to put it together in order to connect more terminals to a bus. Okay, that covers CAN bus. We're happy for questions. If there are any right now, if not, you can always email them. And thank you very much.
Well, thank you, everybody, for joining us today. For those of you who are interested, tomorrow at the same time, we are doing ARINC-429 and ARINC-717. Once again, if anybody has questions, please contact me by email, and be happy to answer them. If you have any questions regarding our products, please contact me. And have a nice day, everybody, and thank you for joining us.
Bye.